So now let's look at another question on finding the stress at critical point. Okay. So the specialty of this question is, unlike the last problem, it was we have three condition: axial load condition, bending load condition. It was individual. Basically, all these three cases was individual. There was not combined loading effect. But in this question, we have both bending and axial load one at a time. So how do we solve such problem? So we have a shaft which has a bending load of 3 kilonewton and an axial load of 15 kilonewton. As shown, you can see the figure. It's having a diameter of 60 mm, while the length 300 mm. All you have to do is determine the stress at the critical point. Okay. So now we just write all the given terms. We have a length 300 mm. That force, I am assuming that axial load Pf1, that is 50 kilonewton, and that we converted into Newton, 15 into 10 raised to 3 Newton. Then the bending load to be F2, 3 kilonewton. So by conversion, it will be 3000 Newton. And we have the diameter, okay, that is 60 mm. All you have to do is find the critical point at the or principal stresses at A and B. Okay, stresses at a critical point means we have to find the principal stress at the both the region A and B. So the A and B, this critical point question asks when bending load also come along with the axial load. Okay, just keep that in mind. First step is since we have both the bending load and axial load, we have to find both axial stress and bending stress. So axial stress is simply force by area, F1 by A. Force is 15 kilonewton. So by substituting the formula, sigma D is 5.31 megapascal, while the bending stress sigma B, which is having the formula M by Z. Okay, M is the bending momentum, and the force is F2 into L. That force will be F2 into L. Okay, that's the bending moment because it is due to the force F2L. Okay, then Z is the um, section model is by dq by 32. So formula 32 F2L by 5 dq. Substituting the bending stress will be sigma B equal to 42.44 megapascal. Since we have both bending stress and axial stress, I have to find the resultant stress. Okay, they have to keep in mind whenever we have a bending stress along with the axial stress, in order to find the principal stress, we have to find the resultant because we will be having bending stress will be coming in this direction and axial stress in this direction. So only the resultant among this will have a on both A and B. Just keep that in mind. So we already discussed in the last question to not find the resultant stress at A. So at the point A, it will be having region of tension and B, the region of compression. So since point A having region of tension, sigma A equal to sigma D, it is actually plus, it's error, it is plus sigma B, while and resultant stress at B is sigma D minus sigma B. So we got the resultant stress at both A and B. Okay, then all I have to do is just find the principal stress at both A and B. So let's consider stress at A, where sigma x equal to that resultant stress sigma A. It is 47.55 megapascal, but on the other hand, we know there is no sigma y and sigma xy. So substitute this formula, we get so by using that formula, sigma 1a, sigma x plus sigma y by 2 plus square root of sigma x minus sigma y whole divided by 2 the whole square plus tau square xy. Okay, simply substitute the value, get sigma 1a. Similarly, we can do the minimum principal stress. All difference is the change sign. Okay, if you want to find the minimum principal stress, it would become negative, while is positive. I mean, maximum principal stress will become positive. As you can see, if it adds up only, it become a higher value, right? By using simple logic. Okay, then then you have to find the maximum shear stress. Okay, maximum shear stress. The max is equal to square root of sigma x minus sigma y the whole square plus tau square xy. You get tau max. Okay, tau max equal to 23.88 megapascal. So for first case, okay, we get at point A, the maximum shear stress will be 23.88 megapascal by using the formula square root of tau x minus tau y by 2 the whole square plus tau square xy. Similarly, we can find the principal stress at B by using the same equation like sigma 1b, sigma 2b, and maximum shear stress at point B. We know sigma x equal to sigma b when we consider the principal stress at B, and sigma y is equal to 0, and the tau, there is no shear stress, right? So tau xy equal to 0. So just like we found at point E, we can find similarly the principal stress at point B. So this is how we solve the problem when we have both the bending stress and the axial load condition.